All right, hi everyone, welcome back. The Achieve homework is posted, due after break. The midterm key is posted, so you can review that. And we're going to get through whatever we get through in chapter 15 today, and then we'll continue chapter 15 when we get back from break. The midterm, just looking ahead a little bit. Ooh, I closed out of that. One sec. So we have spring break next week. We have another full week of class, and then the Friday of the following week is our unit exam 2. We will have recitation that morning. I'll add that into the syllabus. So just keep that in mind. That will be chapter 14 that was not on the midterm, so like the second half, chapter 15, and we'll at least start chapter 16. Maybe we'll finish it before. So that will be on unit exam 2. So just keep that in mind. And we're going to start with iClickers today. So I have 3 I've already sent out to your devices. This first one, thinking conceptually about what it means for a reaction to be at equilibrium. I will leave this page up because I know sometimes it's small on your devices. Second one, we've got a reaction and equilibrium constant value. Determine if it lies to the left, right, or neither. And then last one, you are given, it's the same reaction, so you still have the K value, and you are determining the K value for the reverse reaction. So let's get started on that. All of these concepts we discussed in class already this week or last week, so keep that in mind. And yeah, we'll spend like 4 or 5 minutes working on this before we continue. So I'll close at, well, we'll see. By the way, yeah, today is March 1st. I don't know if you all grew up with this, but it's like ingrained in my mind that March is reading month. Like that when I was in elementary school, March was reading month. We had like the book store come to the library. We could like buy books. So happy reading month, everybody. Oh, we would decorate our classroom doors as like a book cover. Did any of you all do that? Some of you? That was fun.
I think it should be live stream.
Oh, thanks. And that's why you can greater than 1 of us. And that will tell you Yeah. They're both, wait, what did you say? No, no, sometimes actually most of the time, concentration of products is not equal to reactions. Both reactions are occurring, but they might not have the same concentration. 1 minute, we got 1 more minute. Okay, I believe this is everybody, so I'll close it here. Okay, so first question, which statement is correct? Let's just talk through each of these. So first one, when a chemical reaction reaches equilibrium, the reaction completely stops. That is not correct. At equilibrium, both the forward and the reaction, sorry, I'm all jumbled. The forward reaction and the reverse reactions are occurring. It's not that when you reach equilibrium, then everything stops reacting and everything just kind of settles down. That's not true. The reaction is still occurring. So A is wrong, not A. Oops. Come on now. There we go. All right, B, when a chemical reaction reaches equilibrium, the forward reaction stops and the reverse reaction begins. Well, the definition of equilibrium is that the rate of the forward reaction equals the rate of the reverse reaction. So that means that both rates are not zero, which means neither reaction stops. So both the forward reaction is still occurring and the reverse reaction is still occurring. So B is also incorrect. C says when a chemical reaction reaches equilibrium, both the forward and the reverse reactions are occurring simultaneously. That sounds correct. We said equilibrium is when forward reaction rate equals reverse reaction rate. That means that both reactions have a rate. That means both reactions are occurring. Let's go to D and check D. When chemical reaction reaches equilibrium, the concentration of the products equals the concentration of the reactants. If this were true, remember that K is equal to concentration of products over concentration of reactants. If those were equal at equilibrium, then K would always equal 1. But we've seen plenty of examples where K is not equal to 1 because the concentration of products is not equal to the concentration of reactants. So that is not a condition for equilibrium. That is possible. It is possible for K to equal 1, but that is not necessary to define equilibrium. Often, concentration of products does not equal reactants at equilibrium. C, when a chemical reaction reaches equilibrium, forward and reverse reactions are occurring. That is correct. So C is our correct answer here. Questions on any of these? Stop me at any point. All right, let's go to the next one. At 800 degrees Celsius, the following reaction has a Kp value of 14.1. Does the reaction lie to the left, right, or neither? Again, K is products over reactants. So it is a ratio. If the ratio is greater than 1, 14.1 greater than 1, that means the concentration of products must be higher than the concentration of reactants. And that's all we're looking for on this slide. Is K greater than 1 or less than 1 or equal to 1? It's greater than 1. So that means we have more products at equilibrium because that is the numerator of K. So that means the reaction lies to the side with the products, which is in the chemical reaction here is the right side. So reaction lies to the right. Last question, at 800 Celsius, the following reaction has a Kp value of 14.1. What is the Kp value of the reverse reaction? Y'all remember what we do to find Kp of reverse? Yeah, we do the reciprocal. So we have K of the reverse is equal to 1 over K of the forward reaction. So that's 1 over 14.1, which is 0.071. So C is the right answer here. Okay, questions on any of these? All right, so just a review of what we did earlier this week. We will continue seeing how we can manipulate K values for different types of reactions. So the next manipulation we'll learn about is when we alter coefficients for a reaction. So on this page, there are two equilibrium reactions. Both have a balanced chemical equation, but one of them has whole number coefficients, and the second one, there's a fraction coefficient. So for each of these reactions, write the Kc expression, so in terms of concentration. Considering products, reactants, coefficients, write those two expressions out. Okay, I'll just start writing them. I know some of you are still writing. For the first reaction A, product over reactant, only product is N2O. And that has a coefficient of 2, so that becomes the exponent. And then reactants are N2, which has a coefficient of 2, so exponent of 2, and then O2 without an exponent. So that's the equilibrium expression for reaction A. For reaction B, we have N2O in the numerator without an exponent because in reaction B, its coefficient is 1. N2, again without exponent, and then O2, exponent is 1/2. So comparing now equilibrium expression for reaction B to A, it's the same except for the exponents are 1/2 of the exponents in A. So compared to A, all exponents are 1/2 of the exponents in A. Looking at the original two reaction equations that are provided, looking at the second one and comparing to A, all coefficients are 1/2. So now we can say for KC, for reaction B, so KC, and then I'm going to use a superscript B to indicate we're talking about the KC for reaction B. This is equal to KC for reaction A raised to the power of the factor that all coefficients were multiplied by. So if you alter the coefficients in a reaction by some factor, then the K value is raised to the power of that factor. So this is another way, again, we can manipulate the K value to calculate K for a similar but different reaction. So all this is summarized on the next page. When coefficients of a reaction equation are multiplied by a factor, the equilibrium constant is raised to the power of that factor. So we first have reactant A forming B, and the K is B over A. If we multiply coefficients by 2, then we can take the original K value and square it, and that's the K value for this reaction. If we multiply coefficients by 1/2, then we take the original K value and raise it to the power of 1/2, and we have the K value calculus. So all of what we've learned about manipulating these K values, either inversing, raising to a certain power, we can use those to then calculate K for an overall reaction that is the sum of individual reactions. So kind of like adding elementary steps for an overall reaction equation, we'll do the same thing, but we're focused on the K values here. So on this next slide, we've got 2 individual reactions with known K values. So we have A plus B forming C, and then D forming 2C. This is resource information is what I'll call it. Or given information that will be used to then complete this problem. This is our goal, to write the equilibrium constant or calculate the equilibrium constant for an overall reaction, which is the sum of some version of those given reactions. Are you with me so far? Any questions? Okay, so we will need to rearrange or multiply, reverse the given reactions to reach this goal. 2A plus 2B forms D. So for the 2 reactants, A and B, we'll use that first reaction, but we need to multiply coefficients by a factor of 2 to get 2A and 2B. So for reactants, we will use the equation 2A plus 2B is in equilibrium with 2C. So we're using the original with the known K value, multiplying by 2 for the coefficients, so that we've got 2A and 2B. So if we're multiplying coefficients by 2, then the K value for this reaction is the given K value, 0.80, squared. We raise it to the power of 2 because we've multiplied coefficients by a factor of 2. Then for products, our product is D. We will use the second equation, but we need to reverse that equation now to have D on the product side. So we'll have 2C forming D. And so the K value, we need to take the inverse of 2.1 over 2.5. That's the K value of the reverse of that reaction, so 2C. The D of the product, K value is 0.4. So these two steps were to ensure that now when we add these two reactions together, the 2A plus 2B forming 2C and 2C forming D, will reach the overall equation that we're looking for here. So we need to double check that that's correct. We'll add reactions together. So just like canceling out what's on the product side and the reactant side, the only thing that's repeated is this 2C, which is on the product here and reactant over here. So we can cancel those out, and the overall reaction is 2A plus 2B forms D, which is what we are looking for. Now you could start here. You could start by thinking, I need to reach this overall reaction. How can I manipulate those given reactions to then cancel certain things out and have the correct coefficients? You know, based on this process, that you need to multiply the first one by 2. So then you'd go over here, multiply by 2, raise K to the power of 2. This one you need to reverse, so then you would invert the K. That's fine too. Go through this problem in that process as well. But either way, once you get here, now we have to think about the K values and what this means. So K for that first reaction, 0.64. K for the second reaction is 0.40. K for the overall reaction, we added these reactions together to get the overall reaction. K values are multiplied. So we'll multiply 0.64 by 0.4, and that will be the overall K value. So let's put words to this process down here. When 2 or more reactions are added together, the equilibrium constant of the overall reaction, so equilibrium constant K, is the product of the individual reaction constant, Ks. And so that's what we did down here. We added the two reaction equations together and then multiplied the two K values. Okay, there were a lot of steps here. Questions on how we go through this? Yes. Yes. I did the reverse for the second reaction because in our target reaction here, D is on the product side. In the given reaction, D is a reactant. So we need to reverse it to have D on the right side. So we did that here, and that means we had to invert the K. Okay, well, to summarize what we've learned in this section, using the reaction constant, so we can calculate K if we know all of the concentrations of products and reactants at equilibrium, or Kp if we know all the partial pressures of products and reactants at equilibrium. If we know the K value, but are missing one product or one reactant's equilibrium concentration or partial pressure, we can use that expression to find the concentration or partial pressure of an individual species. When a reaction is reversed, K is inverted. When coefficients of a reaction are multiplied by a factor, the K value is raised to the power of that factor. So that was new from today. And then when reactions are summed, added together, their K values are multiplied. So that's what we did on that last slide. Oh, I forgot to ask you. Oh gosh. Does this reaction lie to the right or to the left? Lies to the left. The K value is less than 1. So that means there are more more reactants, which are in the denominator, than products at equilibrium. So more reactants means there's more of what's on the left side, so the reaction lies to the left. All right. So let's go to 15.4. So all of what we've done so far in this section, we're assuming that the reaction is at equilibrium. So it has reached a point where the concentration of the products isn't changing, the concentration of the reactants isn't changing, and we're using that property for these equations. But when you first add reactants to a container, it takes time for those reactants to reach equilibrium with the products. Or if you're adding more products, that can alter the equilibrium. So we're going to talk about determining, using the reaction quotient, if a reaction is at equilibrium or not. And if it's not, is it going to then produce more products to reach equilibrium, or does it need to produce more reactants to reach equilibrium? So we're going to use the reaction quotient, which is very similar to the reaction constant. So the reaction quotient is the ratio of products to reactants, where each species is raised to the stoichiometric coefficient from the balanced equation. That's the same definition of K. But the difference, well, before we talk about the difference, let's look at these. For a reaction A plus B forms C plus D, we can calculate Q relative to concentration. that fraction looks exactly the same as how we calculate K. We can calculate Q in terms of pressure, and again, that fraction looks exactly the same as how we calculate Kp. So Q and K, they take on the same form. We have the same equation, fraction looks exactly the same, but K describes the ratio of products to reactants at equilibrium. So the solution is at equilibrium, or the system is at equilibrium, and that is what K is describing. It doesn't matter, remember, how the concentration of the reactants at the start of the reaction, or products at the start. When a reaction reaches equilibrium, it will have a certain ratio of reactants to products. And that will be always true as long as that reaction is at equilibrium at the same temperature. Q is different as it describes the ratio of products to reactants at any time. So the reaction might not be at equilibrium. We can't use K, so we use Q. So Q describes ratio of products to reactants at any time during the reaction. So then we can compare, let's say you have a reaction equation, you know what the products and reactants are, you have a K value, and you have a measurement of the concentration of everything at a certain time. Knowing the concentration means you can calculate Q, but you won't know if that reaction is at equilibrium until you calculate Q and then compare it to K. If Q is equal to K, that means your reaction's at equilibrium. But if it's not equal, then the reaction has not reached equilibrium yet. So this next slide has these three column images. Let's separate them. Just for explanation purposes, I'll call these 1, 2, and 3. For 3 different conditions. So K, let's look at this middle part of the picture first. So 2. If Q and K are equal to each other, that means that at this point in time, the concentration of products, or the ratio of the concentration of products to reactants, is the same as the ratio at equilibrium. So remember Q concentration of products over concentration of reactants. So if that ratio equals the K value for a reaction, then the reaction's at equilibrium. If Q is less than K, that means that at that point in time, there are more reactants. We have a larger denominator, pointing to the top right corner. We have a larger denominator and a smaller numerator than at equilibrium. So this means that there are more reactants than there would be at equilibrium. So the reaction is not at equilibrium yet. The reactants need to continue to react to produce more product. So that's Q is less than K. If Q is greater than K, then there is a larger numerator, more products than there would be or should be at equilibrium. So the products will react to form more reactants. And the reaction will proceed to the left side, the reactant side. Q is less than K, the reaction will proceed to the right to form more products. So we are, just to summarize, comparing the value of Q to K. So you would calculate Q and be given K. And then if Q is equal to K, then you know the reaction's at equilibrium. If Q is less than K, there is not enough product present, so the reaction will proceed to the right to form more product. If Q is greater than K, there is more product present than there should be at equilibrium, so the reaction will proceed to the left to reproduce more reactant and use up the product. So let's look at an actual example here. at a certain time. So this means we don't know if this is at equilibrium. It's not stating that it's at equilibrium. At some time. Concentrations for each species in the reaction below, we've got an equilibrium reaction, are 0.32 molar for bromine, 0.37 molar for chlorine, 0.15 for BrCl, bromine chloride. Is this reaction at equilibrium? And then if not, which direction will the reaction proceed? What's our first step here? We have to calculate Q, yes. We need to find the ratio of products to reactants and see if that equals the ratio of products to reactants at equilibrium, the 377. So we write out the expression for Q, concentration of bromine times concentration of chlorine, divided by concentration of bromine chloride squared. And we plug in values to calculate Q. Okay, then simplifying this fraction here, the value of Q is 5.3. So we have Q, we have K. Think and discuss with classmates around you. What does this mean? Which direction is the reaction at equilibrium? And if not, which direction will it proceed? To form more products, so to the right, or form more reactants to the left? Okay, so we have Q is 5.3, K is 377, Q is much smaller than K, but all that really matters is that it is smaller. Q is less than K. So this means that at this time, we have a lower concentration of products than at equilibrium. It also means, by default, that we have a higher concentration of reactants than at equilibrium. And we know that because Q is concentration of products over, products over reactants, and this value is smaller than K. So for this value to get larger, we need to decrease the amount of reactants. or in other words, the concentration of reactants is too high, and we need to increase the concentration of products, or in other words, at this time, the concentration of products is too low. So we have lower products than, or lower concentration of products than at equilibrium, higher concentration of reactants than at equilibrium. So the reaction will proceed to correct that, to increase the concentration of products, decrease the concentration of reactants, which means the reaction will proceed to the right, to the product side, to produce more product and use up more reactants. That is required for the reaction to reach equilibrium. And one important thing that you can write on this slide, you can write on the previous slide, I'm writing it across the top here. Reactions always tend toward equilibrium. When a reaction is at equilibrium, it's in a lower energy state. It's stable, it's happy. It will not go out of equilibrium unless something changes, like the temperature changes or some more products are added to it or more reactants are added to it. Then it will shift out of equilibrium and then reestablish equilibrium. So reactions always tend toward equilibrium, and that's how we can determine which direction the reaction will proceed. Yes?
Does Q have units?
No, just like K, it doesn't have any units. Yeah, good question. Yes.
So only at equilibrium will lie to the left or smaller?
So if Q is greater than K, then it would lie to the left, because that would mean it has more products at equilibrium, so it would need to proceed left to use up the products. If Q is equal to K, then we know it's at equilibrium. But if Q is not equal to K, it's not at equilibrium. The reaction will either produce more product or more reactant to reach equilibrium. Other questions? Okay. So we're going to cover the first few slides of this next section, where we'll talk about ice tables. So in the past, we know a reaction is complete for irreversible reactions when the limiting reactant is used up. So we talked about this last term, or in Gen Chem 1, you talk about limiting reactants. The reaction is over when there's no more reactant to react. So an example of that is a combustion reaction, or let's just write combustion. Think about a bonfire, like a combustion reaction. We call that irreversible because if you're burning a log, it is forming carbon dioxide gas, it's forming water, we've got ashes. We can't combine, or I guess we could, but it'd be very difficult to combine all of those together and reform a log. Right, so that's an irreversible reaction. So we know that's over when the limiting reactant is used up. We can also tell how much product will be present based on the amount of the limiting reactant. But if we have reversible conditions, the reaction really isn't ever over. We can think about it being over or stable once it reaches equilibrium. Then we're not seeing any change in the amount of products or reactants. So for reversible reaction, reaction is complete when the reaction reaches equilibrium. So how if we know how much reactant is added, we have to consider what equilibrium means for that reaction in order to calculate how much of each reactant is still remaining at equilibrium and how much of the product is present at equilibrium. For that, we'll use an ICE table. So we're just going to go through this slide. You have one achieved question with an ICE table. We'll continue talking about ICE tables after break. So here's an example of an equilibrium reaction. Hydrogen and iodine forming hydrogen iodide. If we have 0.5 molars of H2, 0.5 molar I2 reacting at high temperature at a constant volume, the amount of HI present that is formed by these two at equilibrium is 0.9 molar. But remember that not all of the H2 and I2 is completely used up. There's still some present at equilibrium. So we can use an ICE table to determine that amount, how much of H2 and I2 are present at equilibrium after some of the HI is formed, however much should be formed at equilibrium. So ICE table, we call it an ICE table because we have 3 rows, initial, change, equilibrium, ICE. The initial, we know initial amounts of all 3 of these in this question statement. We have 0.5 molar H2, 0.5 molar I2, and 0 HI. The reactants are forming the product, so we don't have anything at the start. We also know that at equilibrium, the concentration of HI is 0.9 molar. It says 0.9 moles, but we're in a 1 molar container, so 0.9 moles per 1 liter is 0.9 molar. So that's everything that's given. Then we will have a variable to describe how the concentrations of each of these change. So H2 is used up. It's a reactant, so it is used up by some amount, and we're just going to call that X. So the change is minus X. Minus because that's a reactant that will be used up, and then X for our variable here. I2, well, H2 and I2 are in a 1-to-1 ratio, so for every mole that's used up for H2, the same amount is used up for I2. So the change for I2 is also minus X. And then HI is produced for every 1 mole of H2, 2 moles of HI are produced. These are the coefficients in the reaction, the balanced reaction. So the change for HI, we're increasing the amount, so it'll be positive, and then coefficient of 2, so we have plus 2x for the change for HI. So for every mole of I2 used up, we have 2 moles of HI produced. Or every mole of H2 used up, 2 moles of HI produced. Okay, so once you have all of that added in, we can use a column to solve for X. So HI starts at a concentration of 0, increases by 2x, and then ends at 0.9. So for this column, we have 0 plus 2x equals 0.900 molar. So X is 0.450. So now that we have the value of X, this variable that describes the change in amounts for reactants and products, we can use that to find equilibrium concentrations of H2 and I2. So for H2, we know X is 0.450. Then we have 0.500 minus x minus 0.450 equals the equilibrium concentration. I'm just going to put capital E for that, for H2. Simplifying the left side, that's 0.050. So at equilibrium, the concentration of H2 is 0.050 molar. And we calculate that by first finding x and then setting initial plus the change equals equilibrium. We would have the same equation for I2. We start at 0.5, we subtract 0.45, and we'll have 0.05 at equilibrium. So knowing initial concentrations, the ratio in of each species in the reaction equation, and the final concentration of the product, we can then determine how much of each reactant is present. And knowing all three of these concentrations, we can then calculate K. So we can find the K value now that we have all equilibrium concentrations. Okay, we will continue this. Have a wonderful break. I'll see you all in a week and a half.